These geologic events are the result of forces bending and straining within the Earth's crust. If they occur where man-made structures have been built, the results can be catastrophic. Engineers and architects have been trying to understand the effects of earthquakes on structures for many years. Scientists have been studying how and why these tremors cause tremendous damage. Working together, scientists and engineers are looking for ways to design and construct buildings that can survive an earthquake. In this activity, you will construct a model building that will withstand the tremors of a simulated earthquake using an EQs Tremor Table. Just like engineers, you will test the effects of an earthquake on your model structure and observe the forces which will shake the structure until it collapses. This activity simulates a 15-story, 150-foot tall building, measuring 40 feet by 40 feet at the base. A real building like this would weigh about 1.25 million tons, so 5 wooden floor plates would be built into the structure. The addition of mass plates to each floor will simulate the mass distribution to scale. In order to get started with our project, you will need to gather some supplies. This is our list of recommended materials, but you should check with your teacher, as he or she may want to adjust them for your particular class.
The study of earthquakes is called seismology. The name comes from 2 Greek words, seismos, meaning earthquake, and logos, meaning study.
Before you start building, you will want to refer to any specifications your teacher has provided for your tower. As you design your tower, you need to consider the number of floors, the total height, the amount of materials you want to use, and other factors as specified by your teacher. Your tower will need to connect to the EQs Tremor Table by means of a foundation block and a tower base block. Notice that the tower base block has slotted holes to provide quick mounting to the EQs Tremor Table. For basic tower building, we recommend that you build the tower around the foundation block, attaching the completed tower to the tower base block for testing. So the first thing we need to do is measure the length and width of the foundation block. You will use these measurements as you design and build your tower. In this activity, we will assume the foundation block is the standard size, 19 millimeters by 96 millimeters by 101 millimeters.
According to the U.S. Geological Survey National Earthquake Information Center, the worst earthquake in history occurred in 1556 in the city of Shanxi, China, where 830,000 people were killed.
It's time to get started. To begin, we will first sketch 2 identical side views of your tower design on paper. The paper must be large enough to accommodate 2 sides of the tower. Each side will be approximately 10 centimeters by 50 centimeters. You may have to tape 2 sections of paper together. For a standard tower, these two sides should be rectangles, 10.1 centimeters wide and 50 centimeters long. Make the width of the lines for the sides of these rectangles 3 millimeters to show the width of the balsa strips. On this step, we will just draw the outlines and will fill in the floors on a later step. To ensure the tower sides are drawn the correct width to fit the floor plates, hold a floor plate up to the drawing and see if the tower sides you drew align with the notches on the floor plate corners.
The best-known Greek temples were constructed between 480 BC and 323 BC. Many of these temples were built on foundations designed to be resistant to earthquakes.
Next, we need to draw in the floors for our structure. For the standard 5-floor tower, we will space the floors out to 10 centimeters between each floor. On your drawing, measure down from the tower top and draw a 3 millimeter wide line indicating the position of each one of the floors. In this drawing, the top floor will be at the very top of the tower. There should be floor plate lines at 10 centimeters, 20 centimeters, 30 centimeters, and 40 centimeters from the top of the tower. Approximately 10 centimeters will be left at the bottom of each tower side.
The place where an earthquake originates is called the focus. The point on the surface of the Earth directly above the focus is called the epicenter.
Now we're ready to draw diagonal bracing for the two tower sides. The bracing should be identical for each tower side to ensure symmetry or proportion within the structure. The number of diagonals and their placement is a design factor that you must determine for your tower. Draw all diagonals as 3 millimeter wide lines, the width of the balsa strips.
Dr. Charles Richter, an American seismologist, developed a logarithmic scale called the Richter scale to measure earthquake magnitude using numbers between 0 and 10.
Now that you've finished the drawing, we're ready to tape it to the paper-covered foam board. Once the drawing is secure, we will then tape waxed paper over the drawing. This will allow us to construct our structure on the foam board using our drawing as a template.
Most structures use triangles or arches in their design because they are the strongest shapes.
It's time to build the structure. Beginning with the long sides, measure the length of each piece needed, mark a piece of balsa at that length, and cut the balsa piece. You will need to place the piece over the drawing to be sure it is the correct length. Once the piece is the correct length, we will use pins to hold it in place on the foam board. Do not push a pin through the balsa wood because it can split the wood. Instead, we will use 2 pins crisscrossed over the balsa stick to hold it in place. At this time, measure, mark, cut, and position all the long pieces in place using pins.
Stress is the measure of the amount of force placed on an object. When an object is placed under stress, it will change in shape. The amount or distance it changes under stress is called strain or deflection.
Once the long pieces have been cut, you are ready to work on the diagonal braces. Just like the long pieces, you need to measure, mark, and then cut the braces. These are a little bit different in that one or both ends of the piece may have to be cut at an angle for correct fit. Using the timber cutter, you can first cut your piece to the approximate length and then come back and make the actual angle cut. Once that is completed, fit the brace over the drawing, making sure the brace does not invade the space that will be taken by the floor plates. Remember, the position of the floor plates are indicated by the lines perpendicular to the long side piece.
The largest U.S. earthquake occurred in 1964 at the Prince William Sound, Alaska. It measured 9.2 on the Richter scale.
Once you know that the brace fits correctly, add a small amount of glue to both ends and position it on the drawing. Again, we will use pins to keep the brace in position. At this time, you should be ready to repeat this procedure for the rest of the diagonal braces. As soon as you have positioned and glued all the braces, you will need to let the two sides of the tower dry overnight. If you finish this step early, you might help someone sitting near you get caught up.
After a strong earthquake, there are usually several more quakes, or aftershocks. They can be nearly as strong as the original jolt.
Okay, so the glue on your structure brace should be dry, and we're now ready to move on. The next thing we're going to do is to mark the position of each floor plate on each long piece of the tower sides. Carefully lift the two sides from the waxed paper and position one of the sides on the waxed paper so that one long edge is placed over a long edge of the drawing on the waxed paper, and the tower side is vertical, like we've demonstrated here. By placing this side over the drawing, you will ensure square angles as the tower is constructed. After everything is lined up, we're going to pin the side in this vertical position.
Every day, there are approximately 2,600 earthquakes occurring somewhere in the world.
Now that we have one side in position and pinned, we are ready to place the foundation block at the bottom of the tower side. Be sure to orient the block so that it fits evenly with the structure's side. Add glue to the edge of the block that will be against the tower side, and position the block so the bottom of the block is flush with the bottom of the structure's side.
Florida and North Dakota have the fewest earthquakes in the United States.
Now that we have the foundation block in place, we can go ahead and begin to position a floor plate to the tower side at one of the floor plate marks. Remember that these represent the various floors on our building model. You will need to add a small amount of glue to the two notches that will contact the tower side and insert the floor plate into position against the tower side. Be sure that the floor plate is aligned with the marks on both long pieces of the tower sides. Use pins to hold it in place if necessary. Here's a little hint. If the floor place notches are too tight to fit between your tower sides, use sandpaper or a hobby knife and carefully remove just enough wood from the notches to make the floor plates fit between the sides. Once you have the plate positioned, you can use the right angle tool to make sure that it is perpendicular with the foam board. After you have the first floor plate attached, you simply repeat this same procedure for all 5 of the floor plates. You may want to use tape on some corners to ensure stability until the glue dries.
Seismologists record earthquake vibrations in the form of waves known as primary or P waves and secondary or S waves.
We have one side of the structure assembled. Now it's time for the other side. Our next step is to place glue along the front edge of the foundation block and in the remaining notches of the floor plates. Place the other tower side against the foundation block and into the notches of the floor plates, being sure to position the floor plates at the correct position along the tower side. Slide the structure side so that it is in position over the drawing, making sure the tower sides and foundation base are at right angles. This will ensure the structure is square. After you have positioned the second side, pin it into place.
Magnitude is the actual strength of an earthquake. Amplitude is the amount the ground moves as a wave passes by.
At this point, we're ready to add more braces to the structure. Measure, mark, and cut diagonal braces to fit between floors connecting the 2 existing sides on the bottom side of the tower. Just like we did earlier in the process, we will need to fit, glue, and pin each brace into position. Once these braces are in place, you'll need to allow the structure to dry for an hour.
There are 5 types of stress that can be placed on an object: compression, tension, shear, torsion, and bending.
After the glue is dried for an hour, we can reposition the structure in order to attach braces to the remaining side. First, we need to remove the pins and carefully rotate the tower so the final side is positioned down on the waxed paper. Next, we're going to repeat the steps we followed to add diagonal braces to the last side of the tower.
Scientists have determined that the Earth has a thin outer crust, about 22 miles thick under the continents, and about 3 miles thick under the oceans.
At this point, we're ready to attach our structure to the tower base block so we can place it on the tremor table. First, you need to locate the tower base block with the slotted holes and position it so that it is centered on the foundation block at the base of the tower. Mark this position on the tower base block. Next, we will apply glue to the bottom of the foundation block, place the tower base block back into the marked position, and press the tower base block firmly to the foundation block. Again, we're going to place pins at the bottom of the tower base block and clamps, if available, at the top of the foundation block and tower base block to keep them held together tightly. Before moving to the next step, we will need to allow the tower to dry overnight.
Most earthquakes leave evidence of their occurrence, often as a crack called a fault. Earthquakes often reoccur along the fault line.
Now that the tower is constructed, you can add mass plates to each floor to simulate the loading of concrete and steel within a real tower. For each floor, a bolt, load plates, washers, and a wing nut are added to the floor by means of the hole in the center of the floor plate. Your teacher will provide guidelines for the number of load plates to use for your tower. Or you may experiment with various loads for different floors and frequencies of earthquakes using the EQs Tremor Table. To add a load, place the number of washers you want to add on top of the floor, aligning the washer holes with the floor plate's hole. Thread the bolt through the washers and floor plate. To hold the washers onto the plate, tighten a wing nut on the end of the bolt.
The boundary between the Earth's crust and mantle is called the MOHO.
Your structure is finally complete and ready for testing. A step-by-step demonstration of how to use the Pittsco EQs Tremor Table follows in the next section. If you have additional questions, you can refer to the Earthquake Engineering book or contact Pittsco Customer Service. To set up the EQs, first plug the control box cord into the 6-pin jack on the side of the tester. Place the control box where the cord is not pulling against the jack and where the operator can easily reach and see it. Next, plug the EQs power cord into a standard 120-volt outlet. The LED display on the control box should light. Next, you're ready to attach the tower to the table. Place the structure attached to the foundation block and block base on top of the EQs tester. Line up the cutout slots in the base so you can see the anchor holes underneath the base. Place a washer over each hole and thread the anchor through it and into the EQs tabletop. Screw the anchors into the anchor holes, but do not over-tighten the anchors because this could strip the threads in the anchor holes. When testing a structure on the EQs programmable tremor table, anyone near the tester should wear safety glasses. There are 3 modes for the EQs tremor table: manual, record, and play. In this activity, we will cover the manual method. To learn more about the record and play modes, consult the EQs Tremor Table Manual. Make sure the switch on the front side panel of the control box above the LED display is in the middle position. Move the rate slide control to the bottom, or minimum position. It's important to note that the rate slide control does not directly determine the LED reading. This is communicated from a sensor on the tremor table to the LED display. To activate the table, hold down the Start button on the control box. While doing this, move the rate slide control up toward the LED display to increase the frequency of cycles per second, or down to decrease the frequency. When you want to stop testing, release the Start button. The tester will stop, and the frequency at the time the Start button was released will appear on the display. The frequency will remain on the display until the Start button is pressed again.
Just like engineers, you built a model structure and tested its capacity to withstand an earthquake. You may have chosen to test the effects of increasing frequency on structures carrying the same mass. Or you may have tested the effects of increasing mass while maintaining the same frequency. No matter what aspect of your structure's design you focused on, the destructive testing you completed using the EQs Programmable Tremor Table should give you a better understanding of your structure's stability. You may also relate some of the experiences you've had during this process to assignments given in math and science. I hope you've enjoyed building and testing earthquake-resistant structures. For more information on other Pitsco products, check out www.pitsco.com.